This one-dimensional plot is the first window through which we can access the tonal field. This part of the software tool lets us engage with a single mathematical function that generates the entire tonal field. This button, located in the toolbar, labeled G of X, toggles on and off the visibility of this generating function. I'm going to click on the G of X button and turn it on now. This function, G of X, equals sine x times cosine 6x, generates a single geometric object in the form of a continuous curvature. Sampling this curve at 12 of its critical feature points provides a description of the complete structure of tonal expectation within the 12-tone system. All of the intervals, chords, modal scales, half steps, whole steps, and key center modulations exist as feature locations and paths along this continuous curve. Before we discuss the specific tonal features in detail, I'd like to briefly explain the two factors which produce the G of X curve. The G of X is the product of two factors sine x times cosine 6x. The tonal field software tool allows us to plot these two factors so that we can observe how the interference pattern they create forms the features of the G of X curve. This two-factor interference pattern is a form of amplitude modulation in which cosine 6x is referred to as the carrier and sine x is referred to as the envelope. So first, we'll take a look at cosine 6x. So I'm going to switch off the G of X for now, and I'm going to come over here to the toolbar and find the button labeled carrier and switch it on. Now we see the carrier wave cosine 6x. And in order to contextualize this, I'm going to go over to the right-hand side of the toolbar, and the button that says Labels opens the Labels panel. I'm going to switch on the first of the axis labels, radians. And this puts radian labels along our x-axis here. We have at the origin 0, then pi over 2, pi, 3 pi over 2, and 2 pi, one time around the unit circle. And I'm also going to switch on, while we're here in the labels panel, the 12-tet grid lines. And that divides the 2 pi period into 12 equal divisions. If we take the 2 pi period to be our octave, this is similar to how 12-tet divides that octave into 12 equal spaces. And we can see that the cosine 6x completes its cycle 6 times over the course of the octave. And in between each of those, there's a negative peak. So in terms of half steps and whole steps, the cosine 6x does a pretty good job capturing the behavior of a chromatic scale, flipping its sign at every semitone. But this is not enough to get us 12 tones. For that, we're going to need to modulate this chromatic scale by the envelope. So I'm going to switch on the envelope, sine x. So sine x is just a single sine wave, the quadrature partner of the cosine wave, but at the frequency of 1 cycle per 2 pi period. So what's going to happen here is these two waves are going to multiply. That's how waves interact when they occupy the same space. They multiply. And if we look at the plot, we can tell what's going to happen along the way. At the origin, sine x is 0, while cosine x is at 1. So this peak is going to be multiplied and forced to 0. Then it's going to be slowly scaled as we go up. When the cosine wave crosses 0, it'll be negative, but it'll be pulled up by the sine wave. It'll be the negative part will be shrunk as it multiplies by the sine wave, which is not yet 1. That's true for this peak as well. Peaks less than 1 will be attenuated, both positive and negative on this side of the plot. Here at pi over 2, sine x reaches its full peak, 1, so the cosine wave will reach its full negative peak at negative 1. Then it will have the mirror opposite of what just happened for the next 90 degrees through the cycle. These peaks will be attenuated, both the positive 1 peak here will be reduced and the negative 1 peak will be reduced. So in other words, it'll be pulled upward on the plot. Here at pi, exactly halfway across the octave, the location of the tritone, the peak will be forced to 0 again as the sine envelope crosses 0. And then on the other side of this critical point, we will have negative sine x values. And so what that's going to do, because these values are not just scaling between 0 and 1, but they're going between 0 and negative 1, the negative sign of the sine wave here will flip all of the cosine carriers' values. So negative peaks will have a negative number, and when we multiply two negatives, they become positive. And likewise, the single positive peaks here will multiply by a single negative, and they'll become negative. So essentially, we'll get the same picture on the right-hand side between pi and 2 pi as we have between 0 and pi, but it will be vertically flipped on the on its axis here. And that describes precisely what happens on the other side of the tritone when you're going through a diatonic scale. We're going to see that in some more detail in just a moment. So let me go ahead and click on the g of x again, and you'll see how the pattern I described shows up as the gold curve g of x. There we have it. On the left-hand side, the peaks are the same sign as the cosine peaks, but they're attenuated by the envelope. Then they're forced to 0 in the center, and they come out the other side with the opposing sign. So I refer to this as the Tritone Flip. So now we're ready to talk about how the features of the g of x curve give us the features of musical tonality. For that, I'm going to switch off the carrier just so the plot stays clean, but I'll leave the envelope on because it's very interesting to see that our features are where the g of x curve extends to these points and touches the envelope. Essentially where the g of x slope is 0. And there's also two very important features where the sine x crosses 0. So essentially we have 10 lobes and 2 0 crossings are our 12 features. So now we're ready to talk about how the g of x curve features match the features of musical tonality. And for that, I'm going to come back up to the toolbar and click on this button labeled Solfege. That adds points to the features of the g of x curve that are labeled according to solfeggio. And I use solfeggio in my teaching because it captures the relative relationships between tones. I'm going to go over to the labels panel, and I'm going to turn on a few more labels at the bottom. I'm going to click on chromatic letters, and I'm going to click on 12 tet frequencies in hertz. And if we look toward the bottom here, we can see I've added 2 more rows to the 12 equal divisions of the octave. These correspond to the chromatic letters F, F sharp, G, G sharp, A, and the frequencies in hertz which are attached to those letters. It's showing one particular octave, octave 3. I could switch it to octave 1 or bring it up to octave, well, it's going kind of fast. Let's go to octave 4. Octave 4 gives us our classic A440. And these numbers are just, you take any number, and in order to step by, it's a simple equation. You type, you multiply by the 12th root of 2, which is like 1.0595, I think, and it repeats a long time. But if you multiply those, that gives you the frequency values in hertz for 12 tet. And the whole point here is that these are ways of labeling and identifying specific pitches in the pitch space. They don't do a great job of capturing the tonal relationships, because the truth is A can be anything, B can be anything, C can be anything in terms of tone patterning. They can be the tonic, the dominant, they can be inside the key, outside the key. You know, what matters in our musical language in terms of the tonal component is the relationships. And I can demonstrate this. If we go up to the top of the toolbar here, we have our rotations panel, and we have 2 types of rotation. Let me close the labels panel for now. The 2 types of rotation we have are letter, which I would call chromatic rotation, and solfeggio, which is modal rotation. So if I change the letter rotation from, right now it's reading F equals Fa Lydian. Fa and Lydian are somewhat equivalent. I like to just say Fa because it's shorter. But Lydian is a term in common use, the sort of 7 church modes. So those will all show up here too. The idea here isn't to get everyone to adopt my labeling system. It's to show that the labels don't matter, that the curve itself, the tonality itself is an invariant, invariant structure that doesn't matter what we label it. We'll see it, describes the pattern of our expectations, what we hear. So let me drop down the chromatic rotation. I'll change it to C Lydian. And you see what's happened. All of the x-axis has shifted to bring C in line with Fa. And that means that D will be Sol, E will be La, F sharp will be T, G will be Do. And that's, C Fa or G Do, G major, if you want to be very reductive about it. I tend to not be that reductive in my teaching because I feel like it doesn't serve anything. To use generic terms like major and minor to describe a key, you're almost going out of your way to hide the structure from in talking in those terms. So I really prefer to just use this simpler term C Fa. That gives us the anchor point in the chromatic system, and it tells us the mode that we're talking about primarily. So here I can show, if I rotate away from C Fa, like let's go to C, if I go to the Do rotation, it'll also change the chromatic. It kind of supersedes it, so it'll move it to whatever is currently Do will move to the origin. So here we have G Do. And we can have the Sol of that key, which is D Sol. And you see all that's happening. We're not changing the structure when I do this. It's just moving over. It's just rotating. The G of X equation here is getting a little bit complex when I move it to some of these rotations because it's dynamically updating based on what would really make that part of the curve be 0. So there's these phase shift components. And that also is telling. It's showing us here that at me mode, G of X equals negative square root of 3 over 2 times sine X plus 1/2 cosine X times cosine 6X. Those terms are all in there when we go to something like Fa, or Re, the orthogonal anchors of this curve. But at those orthogonal anchors, those phase terms either go to 0 or cancel. So the equation gets much simpler, and that makes sense. Interesting, when we go to Re mode, instead of sine X times cosine 6X, it's cosine X times cosine 6X. So any of these are valid descriptions of this curvature. They're just seeing it from different perspectives. And that also deeply relates to how tonality works. The modality and key and modulation is a matter of your current expectation and how it can change and rotate and recollapse into a new orientation, a new key center or a new modal root. So we'll talk more about that in a moment. Let me switch back. We'll go back to F Fa. Okay. And let me step through the solfege here because I think it's sort of unique, but it's very significant. So when I say that the solfege is mapped onto the G of X curve, or the G of X curve describes the solfege, let me show you what that means in a very practical sense. If I start at Fa, to get to Sol, I go 2 half steps, you see, from Fa to Sol. And in between, the curve dives down into the negative here. That's the chromatic tone that exists between Fa and Sol. But rather than just calling it a black key or an alternation, or Fa sharp or Sol flat, we can do that. But it has a more substantial relationship to the curve. I've chosen to label it anti-Do because it's a tritone away from Do, and it's the exact same magnitude, but the opposite sign, and the same slope. So if we're taking into account slope and magnitude of these feature points, we have 12 unique features that map all the 12 tones in a unique way that captures not just where they are, but how they relate to all of the other 11 feature points. So it's a snapshot that tells us everything about tonality, again, from a simple interference pattern. So let's continue. So if I go from fa to sol, I have this dip here. From sol to la, there's the same whole step transition, but the path the curve takes is much longer because anti-re is a full swap all the way to -1 and all the way back. Incidentally, if you want to see the actual values for these, the y-axis values, we can go to the labels panel and we can turn on g of x values. And this shows the rounded decimal values for these. So they're pretty interesting. I'll have to do another video about exactly where these come from, but you can see that they all have symmetrical partners, and well, we'll get more into that later. But from sol to la is a whole step. From la to ti is a whole step, right? Then from ti to do, because of the tritone flip, ti to do is a half step again, right? So we're back into from ti to do, we go from this 0 point to the next positive value. Then we have the opposite side here. We have do, re, and mi, all whole steps. And then we have the other half step of our scale, mi, fa, as we approach the next 0 crossing. So we have our two half steps that have an opposite phase here. That explains how it captures the behavior of the a 7-tone diatonic scale. But even deeper than that, it shows us something that when we divide up our expectation of the 12-tone system isn't just 7 and 5. It's actually 5 plus 5 plus 2. Let me explain. I'm going to turn off the g of x values for a moment. And what we have is the 2 0 crossings, fa and ti. If we're in the key of C do, then we're talking about the positive values, and plus these 2 zeros are all the white keys. And the negative values are the 5 black keys. The keyboard symmetry is described right here by this pattern. Okay? So, and it tells us more than the keyboard symmetry, because it tells us that in this case, F and B are different than C, D, E, G, and A. C, D, E, G, and A are the pentatonic scale, do, re, mi, sol, la. Fa and ti are 2 axis tones that relate to that pentatonic scale. In fact, fa and ti are a tritone apart, just like all of the other notes are a tritone apart from their antipentatonic partners. I call the negative lobes together the antipentatonic scale, because that's precisely what they are. It's the exact same pentatonic scale transposed away by 6 semitones. Okay, so we have one tritone here that links them together. And in fact, if we were to, the tritone is, because it's 6 half steps, exactly 1/2 of the octave, it's symmetrical it inverts on itself. So there's really nothing inherent to tell us that this couldn't also be ti and fa instead of fa and ti. So if we were to mentally flip those two and consider that ti is, this fa is actually ti, then we would just simply be oriented to take the negative path here. Ti, do, re, mi, fa, sol, la, ti. So the negative part, hemisphere of this g of x curve is a totally valid set of expectations. It's the signage here is just modeling the current orientation of the listener. So when we're oriented in a certain key, we will hear this set as positive and this set as undermining that orientation. But everyone knows if we keep playing those, especially in a way that makes sense, that audiates this key center, eventually, pretty quickly, even without preparation, the listener's expectation will flip. They'll rebuild their confidence. These will become the positive values. These will all become the negative values, and we'll have succeeded in modulating to a key that is exactly 6 semitones away. So this starts to hint at how the g of x gives us not just the ability to modulate between keys that are a tritone apart, but we can actually see how each of these negative values, the black keys, the antipentatonic, how they will allow us to calculate precise modulation vectors to any of the 12 key rotations within 12 tet. And this also describes how we're not, the G of X is not just 12 samples. It's a continuous curve. We can place this Fa T tritone between any two frequencies that are 6 times the 12th root of 2. So anywhere. That's why songs work even when they're tuned in between these half steps. There's plenty of famous examples of hit songs that are tuned by ear or that have been sped up or slowed down after they've been recorded, so they don't correspond to the keys of the piano. And they still perform, they still create fully coherent tonal patterning because they're internally consistent. So this G of X kind of shows us why that is the case. Okay, so that explains the pentatonic and the antipentatonic concept. Let me open something that'll help us see that even more clearly. I'm going to go back up to the toolbar here, and I'm going to click on Dodecagons. And that brings up these 2 circles. These might be familiar to you. They're the same solfege. These are our 12 features, or organized in a circle representation here. The first one is scale order. So that's the order that we see. If we go from the top of the circle, we have Fa, then Do, then Sol, then Re. So as we go clockwise around the circle, that's showing us the scale order here. And then harmonic order is ordering these same elements by the circle of fifths and circle of fourths, depending on which way we rotate. You know, so we see that, and here we can really see how the dominant chain is produced here. Ti resolves to Mi, resolves to La, resolves to Re, resolves to Sol, resolves to Do, resolves to Fa. Those are resolutions by, you know, going up a fourth, basically, or down a fifth. And what we can also see is the antipentatonic fills in the rest of that story. Although Ti and Fa are these kind of special limited axes within a key together. Like we said, these will trigger modulation vectors when we start using them. Now, let me show this. If I click this button up here at the top that says Diatonic, we can get rid of, we can kind of simulate what it is to not be considering the antipentatonics, just considering them black space, you know, like kind of throwing away their G of X values. And also, if I click Grayscale, I'll get rid of the color code. The color code I use, I think it's really useful. It helps us find Do very quickly or Sol very quickly and understand, you know, connect a lot of those things to those colors. But sometimes it's much more useful to see them in grayscale, which just gives them their value based on the G of X value. So Re is the brightest white at +1. Anti-Re is -1. Here, I'll take off diatonic for a moment. And you'll see that the only difference there is that some of those antipentatonics get a little darker when I go to diatonic because it just forces them all to be 0, when in fact some of them are not quite 0. You know, this Do and anti-Do and anti-Mi are -0.5. Anti-Sol and La are -0.8, so they're pretty close, you know. Okay, but either way, when we do that, we can see here on the Dodecagons, we can really see how the G of X values sort the harmonic order into a perfect gradient of luminescence. And we can see the chromatic pattern showing up in the scale order here. So now it's really clear to see where the half steps and whole steps actually are. Re to Mi to Fa to Sol to La to Ti to Do, back to Re. In fact, this also suggests that we should maybe reorder the who's at the top of these circles. I'm going to go back up to the Modal Rotation panel, and I'm going to change it from Fa orientation to Re orientation. Now we can see a couple of things that are very striking. If we look at the main plot, we can now see that it has mirror symmetry at the tritone. Okay. Before we kind of had our flipped, one side seemed like the flipped side of the other one. But when we view it from Re centrality, we can see that we have the exact same pattern going in a mirrored opposite direction once we pass anti-Re. And when we look at the Dodecagons, we see our 2 pentatonic scales, one the in-phase pentatonic is a bright 5-pointed star. The antipentatonic is an equally dark inverted star. And we have our luminescence pattern with ray at the top. And this also shows us our major-minor bifurcation. The slope of the envelope basically sorts do and sol into the positive side, la and mi into the negative side, and re as the center. And that shows how the modes organize themselves. Sol, do, and fa are the major modes. La, mi, and ti are the minor modes, and re is balanced exactly in between the two. It's the center of the piano keyboard symmetry, and so is anti-re. Re is the only white key that has a symmetrical pattern on the keyboard. And anti-re, if we're looking in the key of C do, that's the G sharp, that's the center of the group of 3 black keys, right? So this symmetry is pretty deep, and it's sort of captured and expressed here in the G of X function. I'm going to turn off grayscale and bring back the color code. Okay, so I think we've talked about most of the things. There's a calculator feature here, which is really interesting. It can help us understand some of those things I was just talking about major, minor bifurcation, or also how to build up, basically how to sum certain relationships inside the key. And it allows us to do some calculations and understand how more than one of these tones create the structures like chords and arpeggios, even scales. An interesting one is if I click on do, mi, sol, that's, or I clicked it on out of order. But either way, this is C, G, and E, in the key of C do, this is what's referred to as the tonic triad. And it gives us some information about its slope and about its summed G of X values, basically showing us that this triad is well within the key. It's in the positive hemisphere, all of these lobes. If I wanted to compare it to something, I could create another. I click mode plus, and I can create another structure here. I'm going to do re fa. I'll do T re fa, which is the diminished diminished chord here. Right, its slope is much less than 1.866. It's just a +1, so almost half. So it has less of the stability of being within the key because it's using 2 of the access tones. Fa and T, I color them yellow and pink, and I tell my students it's like lemonade and pink lemonade. You can tell when they're present, especially against something like a pure pentatonic scale. As soon as you touch one of these access tones, we feel it. We feel that we're heading toward that boundary. And if we audiate or sound any of the negative notes, they're even extra spicy, right? So if I add to this T, re, fa, if I add anti-re, that's going to create the completely diminished 7th chord, right? And that's -1 plus 0 plus 0 plus 1, right? That's going to create a net 0. And that's what happens with all the symmetrical chords. The fully diminished 7th combinations and the augmented triads all sum to 0. And that makes sense because they basically don't have key confidence or even root confidence. Everything is undermined. Look, even the envelope slope is 0 here. So all of those, none of this was designed to do any of that or to model any of that behavior. These are all structural behaviors that are coming through here. So let me just clear all this stuff out. I'll close the calculator. We'll talk much more about the calculator when we go to the 2D matrix view. That's really where it comes into play. It's surfaceable here too, so that we can create our chords and things here. This is actually laid out in perfect stacks of perfect fourths, so it behaves just like a guitar fretboard. I can even change the tuning if I want to make it really behave like a guitar fretboard. Change the number of strings. But okay, this is a preview. We'll have to talk about this in the next video. Let me jump back over to the 1D plot view. There's just one other thing that I want to mention on this view, and that's the spectral components. This is sort of an alternate path to the same function, but it comes from some of the trig identities that come into play in signal processing. So let me show you. We talked about how we got this curve from modulation by multiplying the two factors. But there's a trig identity that shows us this in the frequency domain. Basically, the Fourier series says that any periodic signal, no matter how complex, breaks down into the sum of its spectral components. And so this is true here as well. Basically, there's something called the product sum that will show us our g of x from a different algebraic vantage point. And so I'm going to go ahead and turn on the product sum. And it shows us that the same g of x that here equals cosine x times cosine 6x equals 1/2 of cosine 7x plus 1/2 of cosine 5x. And that's really interesting because our factor here that makes the cosine, the envelope, different from the carrier is n equals 6, okay? And the product sum, the way that it works is it says that with that number, the two spectral components will be symmetrical around that number. So in other words, not n equals 6, but on one hand, n equals n plus 1, which is 7, and on the other hand, n minus 1, which is 5. And that captures precisely the perfect fifth and perfect fourth in terms of their semitones. It's truly remarkable. Let me switch them on here. The spectral components are surfaceable here, the 1/2 cosine 7x, the 1/2 cosine 5x. Interestingly enough, by the way, the labels of these buttons are dynamic. So when we're in fa rotation, they're actually sine terms and the sine minus sine. And when they're in re, they are cosines that add. They're the same curve. They're just shifted by 90 degrees. So let me go ahead and turn them on. This is 1/2 cosine 7x, right? Which does its cosine cycle 7 times over the 2 pi period. And this is 1/2 cosine 5x. So that's 1/2 magnitude of the same cosine signal, but it's going slower. So it only repeats 5 times. And you can see exactly, let me turn off the envelope because that's not, now we can see that we get the same curve from adding these two sinusoids. And you can see why. Here at the origin, the 2 0.5s align, and so they become 0.5 plus 0.5 is 1. Here at pi, negative 0.5 plus negative 0.5 makes negative 1. So that forms our extreme ray and anti-ray features. And then in between, everywhere where they're kind of close but not exact, we get these lower lobes, right? And they cross 0 at precisely our two important tritone features, fa and ti. Okay, so that's the product sum that shows us where how we can get the same curve from the sum of those two spectral components, rather. All right, so I think that that about does it for this video explaining the 1D plot view, and we'll come back with the next video where we'll talk about the 2D matrix, and then we'll move on to the object view and the 3D torus view. So look forward to seeing you in the next video.